All right, CalcBC students, let's converge absolutely and talk about the ratio test. Before I share the definition of absolute convergence, I want you to see what absolute convergence looks like. So we're asking the question, why does the Riemann sum of sine x to the fifth over 5 factorial converge for all x? But what this question is actually asking, which we'll take a look at in just a moment, is why does this Riemann sum of sine to the nx over n factorial converge for all x? So what I did was I just graphed a visual of what the series would look like for n equals 5. And what I got was one main thing, and it's going to be a little bit tricky for you to see it, but not that difficult. What we see is this brown curve down here that almost, kind of looks like a sine function, but has this little leveling off that happens by the x-axis. So if I add up all of the terms of this series when n equals 5, I get this, or 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 this. So it's going up here, and I'll explain why the blue curve covers up this one in a moment. But the brown curve goes up and down and down and up and down and down and up and up, like so. Now, the value of the sum of the series just depends on the value of x. And up until this point of your studies in series, we haven't really talked about what happens when we let x be this or x be that. All we really talked about is x having like a center of approximation, x equals a or x equals 0 for Maclaurin. But what I want to communicate with you right now is this. Let's suppose x equals 0. Then that means this series adds up to 0. That's what this graph is telling us, is that the actual sum is 0. But let's say that x equals 1 and n equals 5 in this case. So n equals 5 for this entire visual, and n equals 5, x equals 1. The series is going to add up to this number right here, 0.003. Now that's not super exciting. I definitely don't think so. But what I think is super cool is this visual and what happens. But let's go back to x equals 1. Like, you might be wondering, why is the sum such a small number? And that goes back to when we take the derivative of sine and the second derivative and the third derivative, the value toggles between 0, 1, and -1. So all of these terms of the series are going to change in value. So some will be above 0, some will be less than 0, and they'll change as n gets bigger. All right, so we get this sum to be very small because the difference in those values is not that great. Now I'm going to go way over here to like -4 point something, and now I recall that 4.7 is some multiple of pi over 2, and that kind of makes sense that it would be like a peak of the graph. 3 more little thoughts about this graph before we move on is that the brown curve is actually the Riemann sum of a sub n, just straight up the Riemann sum. And then the blue curve is the Riemann sum of the absolute value of those terms. And that's what connects to the absolute convergence. And the orange line in this case is some value that this series never goes above. In fact, it's the number that is helping us to understand that this series right here converges for all x. And that number is 1 over n factorial, which we'll show in a moment. All right, that was a long intro, but I think it was worth it. Let's talk about the definition of absolutely convergent series. And we'll start with just absolute convergence specifically. And the preface for this is saying that if the series, the Riemann sum of the absolute value of a sub n, of absolute values, okay, so this notation is basically saying the Riemann sum of absolute values converges if the series of positive values converges. Then we say that the Riemann sum of the series in general converges absolutely. So in essence, what we're saying right now is that we don't really have something that tells us that a series converges just based on its natural state. Like just all of the terms, all of the values added together. We can't just say that it definitely converges. But by taking the absolute value of all of the values of the whole series, then we can say that it converges absolutely, and we could use something like the ratio test to show that that series converges. All right, then similarly, or similar to if a function is differentiable, it implies continuity. If a series is absolutely convergent or converges absolutely, then that implies convergence. That means we have this. And it almost seems identical to what we just said. We said that this converges absolutely, but then we'll use something like the ratio test to show that it indeed converges. This series. A series that we're talking about. All right, let's do an example. Enough of that. The example is this. Show that, and this goes back to the original visual, show that this series converges for all real x. Okay, now going back to the visual, this series may have terms that alternate between positive and negative. That means we can apply something like the sandwich theorem back when we learned that in the limits unit, but slightly different, the direct comparison test. First, let's think about what the min would be. The min of this entire series. Okay, in general, because sine bounces between -1 and 1, that means the minimum of this entire series, just thinking about the numerator, would be -1, and then for the denominator, we would just leave that as n factorial. Now the max. Well, that would just be the opposite, so that would be 1 over n factorial. That means sine x to the n over n factorial is going to be in between these values. And that min and max gives us this absolute inequality. So we have the absolute value of the series is less than or equal to 1 over n factorial. Now, we're kind of stuck at this point now thinking about, well, what does that mean and what does that tell us? And so that's where I need to jump in and tell you a little bit about 1 over n factorial. The Riemann sum of 1 over n factorial converges to something special. And now you're like, whoa, where did that come from? All right, let me explain real quickly, and then we'll wrap this example. Well, recall from topic 2 that e to the x can be found as a series by expanding this out. 1 plus x to the 1 over 1 factorial, x to the 2 over 2 factorial, x to the 3 over 3 factorial. And that's just the Maclaurin series, centered at x equals 0, taking the derivative, plugging in 0 for each one of those, and we get the series. Well, what is that in the nth as an nth term? Well, the general term for that is x to the n. We're just raising the x to a power over n factorial. And I could say, like this right here converges to e to the x right here, but we already know that because that's where we originally started from, what I'm basically showing you. But what happens when we plug in x equals 1? We get the Riemann sum of 1 to the n over n factorial. So that's a really specific example of letting a series have a certain x value. That's the first time that we've done that. And so notice x equals 1, x equals 1 right there. E to the 1, there's e to the 1 right there. Okay, so if we know some of the basic functions and what their series are, then we could use them to find out the convergence of other series. Then let's come back to what we were doing already. That now you don't have to repeat some of this, we could just make the conclusion, but if we know that the absolute value of our series is less than a certain number, which, and 1 over n factorial equals e, then our series converges absolutely. Okay, so that's absolute convergence. And let's take a look at that original visual now. We could see that that 1 over n factorial is the upper bound of that blue curve, which is basically the absolute value of that series. And then there's actually a lower bound as well, but we're not really using that. The only reason is because there's not a test that says, kind of like the sandwich theorem, that has a lower bound and an upper bound. We're just trying to make sure that our series is less than a certain number to show convergence. Okay, now for the good stuff, the ratio test. Here it is. So let the Riemann sum of A sub n be a series with positive terms, and the limit as n approaches infinity of A sub n plus 1, that's the next term, divided by the current term, or just dividing two subsequent terms by each other, that equals some limit L. Now, three things can happen with that limit L. The first thing that we like is that the series converges if L is less than 1. And that's just saying that the next term, when you divide the next term by the previous term, you get a smaller number, and that means the terms are decreasing in value. Now, the series diverges if L is greater than 1. That means the terms are getting bigger. So 3, then 4, then 5.7, or whatever. And then finally, if L equals 1, the test is inconclusive. That means that the terms are like 5, 5, 5, 5, 5. You know, the ratio of each subsequent term is 1, or it's becoming 1. So we're just adding up a bunch of numbers that are about the same size. That's the test, all right? And this is a big test. It's one of the most powerful tests. It's one of the tests that will show up on an AP exam almost all the time. And let's do one example of that. And by the way, it's most of what your practice exercises are. We're trying to find the radius of convergence of this particular series. So let's see if we could do the ratio test. We look back at here, the series with positive terms. All right, so if I take n equals 0 and I plug this in, I get 0 times something to the 0, which is 1. So 0 divided by 1 is 0. Okay. Uh-oh. I don't actually think that's going to cause an issue for this test. I never thought about that, actually. Never did that test. But if we plug in 1, then we would get positive values. Of course, if x was a negative number, then all right. So let's just work the test and then see if it works. Okay, here we go. The first thing we want to do is take the limit as n approaches infinity of the n plus 1th term. So that looks like this. N plus 1th term. It's kind of an n plus first, n plus first. Okay, that's x to the n plus 1 over 10 to the n plus 1. And we're going to take all of that and divide that by the nth term, which is just the series as it is, n x to the n over 10 to the n. Aha, here we go. All right, this is the issue. Got it. Okay, going back to that term, if we plug in n equals 0 and then n equals 1, now we have to consider that x could be a negative value, and if we raise it to the 1, we do get negative value. So here it is. This is what we need to do to make all of the terms positive, except for that n equals 0 issue, is that we need to take the absolute value of all of this. Because if we show absolute convergence, then we could show convergence. Now this whole thing is equal to, and we could just do divide by fraction, multiply by the reciprocal sort of thing. And many times in our work, we'll either skip this step right here or write this first step as a product. And so let's analyze this a little bit. We could see that this 10 to the n divides out with this 10 to the n, and so we basically get 10 to the 1. And then we could see that this x to the n divides out with this x to the n there, so we get x to the 1 up there. That means our next step, and we should keep writing the limit because the limit applies to each one, the limit of n plus 1, and that's positive already, so we don't need an absolute value there, but that's x to the 1. Let's scan up here. All right, we got the n plus 1, we got the absolute value of x, we got nothing else in the numerator here. All right, so then the denominator, we have 10 to the 1 and an n, so I'll write that as n, or 10n. There we go. So we have this is a product here, n plus 1 times absolute value of x over 10n. Now we have to apply some of our previous knowledge about limits, is that if we let n approach infinity, that means this n plus 1 is acting in the same way that this n is, and that n plus 1 divided by n is basically 1. That means we have absolute value of x over 10. And that's all of the setup of the ratio test. We're just getting to the point where we have just x as much as by itself as possible, if that makes sense. And then we'll use the steps there for the ratio test to see what's happening. So we want to know, is this limit that we just found, okay, this is L, that's L, that whole thing, is that thing less than 1? And if so, when is that? All right, so let's do that. We're going to take the absolute value of x over 10 and find out when that's less than 1. And that means that we have negative 1 is less than, negative 1 is less than x over 10 is less than 1. That's just the definition of absolute value. If the absolute value of x is less than 1, that means x is between negative 1 and 1. And we can multiply by 10 on both sides to get negative 10 is less than x is less than 10. Now what is this? This right here is the interval of convergence. That means that if x is in between negative 10 and 10, then this entire series converges. But if x was 11, it wouldn't converge. But then what does that mean? We didn't actually answer the question here. Up here it says find the radius of convergence, and that means this is our center of approximation at x. You know, notice that there's no x minus a in this entire series up here. There's no x minus a. It's just x. All right. So that means if x is the center of approximation and x can vary up to 10 and down to negative 10, that the radius of convergence is 10. It's like thinking about a circle, or simply the radius of a circle. Here's our circle or a semicircle, and the radius of that circle is 10. So the answer to our question is r equals 10. Now one more tiny little thing. Basically we have something in the form of x minus 0. So this is the piece. This is our center of approximation. So we have x minus a is less than r is less than or greater than negative r. That goes back to the formal definition of radius of convergence. Okay, thank you so much for watching.